Welcome back to the virtual classroom. This lesson is going to be about the first part of section 4.2, and this PDF file is a blank copy is out on Blackboard, so if you're listening and want to fill in as you go, feel free to download that file and print it out. Of all the chapters in Burton's text, I think that chapter 4 on congruence is by far the most important, and I think most people would agree with me. And of all the sections in that chapter, probably the first real section with mathematical content, section 4.2, is the most important. So arguably this is the most important section of the entire book. Fortunately, it's pretty straightforward, and so let's go through part of it here and then we'll pick up with it later on. The idea is that I start with a fixed integer and then I start talking about two other integers, a and b, and I'll say that a and b are congruent modulo n, or congruent mod n, if n divides their difference. If that's the case, we'll write a is congruent to b, so this triple bar equal is read is congruent to. If n doesn't divide their difference, then the two integers are not congruent or incongruent mod n, and we'll write triple bar not equal or not congruent. So for example, 17 and 5, depending on which way I do the subtraction, I either get 12 or negative 12. Of course, it doesn't matter. Both of those are divisible by 12, and so yes, these two numbers are congruent. You may recognize this example from our clock arithmetic. So in particular, military time, 1700 hours military time is 5 p.m. On a 12-hour clock, the hands would point to the same place at either 5 p.m., 5 a.m., 1700 hours, and so on. Lots of other times as well, of course. So here's another example. This huge, gigantic integer, is it congruent to 1 mod 10? When I take the difference, I get a huge number ending in a lot of zeros, which obviously is divisible by 10. So here's another example of two integers that are congruent, this time mod 10. And the point of this example is to get you used to the idea that depending on what property of the integer we're interested in, we might be able to replace some gigantic number by a very simple one. Let's give the background theorem here to kind of get the entire ball rolling. So if we have a positive integer, the division algorithm says that I can write that as a quotient times the divisor plus a remainder, and the important part is the remainder is non-negative but less than the divisor. So when we talk about congruence mod n, n is going to play the role of the divisor. The remainder then we'll also call the least residue. And so theorem with three parts here. A is congruent to b mod n if and only if the one integer a is the other integer plus some multiple of n. We'll prove that in just a moment. Here's another piece. If I have a fixed integer n, then every integer is congruent mod n to exactly one of the following: 0, 1, 2, 3, da 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 da, up to n minus 1. And of course that's exactly what the definition of least residue is. So for example, 68 is going to be congruent to either 0, 1, 2, dot dot dot, 8, and 9 times 7 is 63, and so 5 more than that takes me up to 68. And finally, two integers are congruent mod n if and only if they have the same least residue. So if I had another integer, big integer, and I wanted to know if it was congruent to 68, one way I could check is it congruent to 5, because I already know that 68 is. So these are pretty intuitive and straightforward but important theorems. Let's go ahead and prove number 1. It's an if and only if statement, and so there are two things to be proven. One is to go in this direction. Here we're going to suppose that a is congruent to b mod n, and we have to show this equality that the one integer is the other plus a multiple of n. So by the division algorithm, we know that we can write A as some kn plus r, where r is less than n, but it's non-negative. And also B, it can be expressed in a similar way. Let's say some k prime n plus r prime, where the same thing is true of r prime. So let's look at the difference between the two. So A minus B, and you see that when I take the difference here, I'm going to have two terms depending on n. Let's factor that out and get k minus k prime times n plus r minus r prime. Now, here's an equation. Is A minus B divisible by n? Yes, that's the very definition of what congruence mod n means. Is the first term on the right divisible by n? Obviously, and therefore we know by now that the last term on the right must be divisible by n. So then n divides r minus r prime. But we know something about r minus r prime. Both r and r prime are greater than or equal to 0 and less than or equal to n. So if you think about taking two integers, say between 0 and 10, and subtracting them and asking how big could that get or how small could that get, this is going to be trapped between negative n and positive n, and with strict inequality here, because I have strict inequality here. All right. So now I have that n divides this difference, but also that this difference is less than n and greater than minus n. There's only one way that that can happen. Thus, r minus r prime has to be equal to 0, which of course is divisible by n, and it's the only integer in this range that is divisible by n. So that proves one direction. I say it proves that. You see that then r and r prime are the same thing, and so yeah, I guess we should add one more step. Then a minus b is k minus k prime times n, because the r minus r prime is going to cancel. Let's go the other direction. Suppose A is Q, let's use K again, is Kn plus R, and B is K prime N plus R. And I'm writing that with the same r because of what I'm allowed to assume, that these two integers differ by a multiple of n. Then their difference is k minus k prime times n. So n does indeed divide the difference, and therefore by the definition of congruence we have that A and B are so. A is congruent to B mod n. Okay, this is almost, I mean the statement of part 1 is almost the definition of congruence, and then 2 and 3 are very much a line. So you can think of this as being 3 different ways of saying the definition, basically. Okay, let's go on to something slightly more interesting. What happens when I start to add and multiply integers? If I start with 2 congruent integers and I add 2 more congruent integers and so on, does congruence carry along with the symmetric and transitive properties and so on that we're used to in arithmetic. So suppose I have A, B, C, D, and this should be an N actually. And N are integers, where N is a positive integer. By the way, we always talk about a positive modulus. And so A and B are congruent mod N, and C and D are congruent mod N. Then the claim is that when I add like this, A plus C and B plus D, the result is still congruent mod N. Same thing when I multiply, A times C and B times D should still be congruent mod N. And exponentiation, when I take A to some power, B to that same power, since A and B were originally congruent mod N, those powers will be. Let's just prove one of these, say number 2. So I have that A and B are congruent mod N and C and D are congruent mod N. So by part 1 of the previous theorem, how can we write this? We know then that A is B plus Kn, and C is D plus, say, Ln for some K and L from the integers. And then let's just follow our nose. What is A times C? Well, it's D plus Ln times, what's the other order, I guess? It is B plus Kn times D plus Ln. And if we FOIL this out, we get BD, and all of the other terms, the other 3 terms, are all going to have an N. So I'm going to multiply out, and immediately in the last 3 terms factor out the N again. And we should get a BL plus a KD plus a KLN all times N. And the question was, is this congruent to, is AC congruent to BD mod N? Well, part 1 of the previous theorem said that's the case when I have an equality where one equals the other plus a multiple of N. So again, by part 1 of previous theorem, AC is congruent to BD mod N. These are pretty intuitive properties, and they do turn out to be true. Some other properties that may seem intuitive later on we'll see actually are not true. So congruence is sort of like equality, but not completely so. Let's do an example of this idea of replacing big numbers by smaller ones. So I'm asked to find the least residue of the integer 33 times 26 squared mod 31. 2 ways of doing the problem: brute force, compute what this actually is, and then use the division algorithm, dividing by 31 and picking off the remainder. Approach number 2. Note that from the previous properties that if I replace A by something that it's congruent to mod N and C by something it's congruent to mod N, then when I add or multiply, the congruence relationship is maintained. So let's mod before we do the computation. 33 mod 31 is 2. And 26 mod 31 is 26. That's its least residue. It's its own least residue. But I can play around with other things that it's congruent to. And in particular, if I'm going to be doing this computation by hand, I'd like the numbers to be as small as possible. So I can freely add and subtract multiples of 31 to maintain something that is congruent to 26. So if we take 26 minus 31, we get negative 5. That's another true statement. And then by 2 and 3 of the above theorem, what I'm supposed to compute, 33 times 26 squared, mod 31 is going to be congruent to 2 times negative 5 squared. And okay, that's, if I'm working by hand, that's much friendlier. So this is 50. I was asked to find the least residue, so now what I'm supposed to do is take this and divide by 31 and take the remainder, which turns out to be 19. So by doing modding before modding down to smaller integers before I do the arithmetic computation, the multiplication and squaring is greatly simplified, and that'll be a huge idea in the course pretty much from now on, actually. Here's kind of an interesting application of modulo arithmetic. Every book published, essentially, every book is given an ISBN number, and since 2007, I believe it's been a 13-digit ISBN number. Before then, it was a 10-digit, and the system worked slightly differently, but with the same basic idea. So here's an example of an ISBN 13. It's a 13-digit base 10 number, and the digits are arranged in information blocks. The first block is an international standards grouping number, which for the most part now is 978. Most of them you see on books now do start with 978. Later on, as more books are published and the agency in charge of ISBN decides to make more use of that grouping, then the first 3 digits will start to have more variety. Next comes a language grouping. So is the book published in English, French, Spanish, or so on? Next comes a publisher number. Then a title number. The title number is assigned by the publisher. The publisher number is assigned by the ISBN standards body. And finally, there's something called a check digit. The purpose of the check digit is to catch errors. So even barcode scanners occasionally make mistakes, but certainly humans do. If I'm keying an ISBN number in by hand into a computer, I might make one of several kinds of errors. For example, miscopying a single digit, maybe transposing 2 adjacent digits. Those are by far the 2 most common mistakes that people make. It's possible to obviously miscopy more than 2 digits in a number and so on, but those are the 2 most common. And by the way, we're talking about ISBN numbers here, but the UPC codes on products in grocery stores and hardware stores and so on work similarly. So the ISBN check digit is designed so that it makes this equality, this congruence rather, true. So if I denote the 13 decimal digits of the ISBN as x1 up through x13, and I form this sum, x1 plus 3x2 plus x3 plus 3x4, alternating with 1, 3, 1, 3, 1, 3 coefficients. The last one will be 1 times x13. If that's congruent to 0 mod 10, then it is a valid ISBN. If it's not congruent to 0 mod 10, it's not valid. And so if a person miscopies an ISBN, whereas before the digits were arranged so that this was a true congruence, if there's a miscopy made, then it's going to adjust the left-hand side and hopefully this congruence will no longer be true, and then the computer will flag that as, oh, there is no such ISBN, somebody must have done something wrong. So here is an ISBN, and some annoying, tricky instructor actually blotted out this digit, and the question is, can we recover that? Maybe there's a smudge on the paper here, or the label got torn or something. Is that digit recoverable? Well, let's see. Let's compute the left-hand side of the congruence above. So it's just brute force. I'm going to do 1, 3, 1, 3 coefficients and accumulate a running total as we go. When we get to this point, I don't know what that is, and so I'm just going to let x stand for the mystery digit that we're trying to find. So 9 plus 3 times 7 plus 8 plus 3 times 8 plus 1 plus 3 times 7 plus 5 plus 3 times 2 plus 5 plus 3 times x plus 6 plus 3 times 6 plus 5. This is valid. The ISBN is valid if x is a base 10 digit, so that this is congruent to 0 mod 10. Let's go ahead and work out what this is. All of the terms except the one containing the x add up to 129 plus 3x. And so what I'm going to do then is set 129 plus 3x congruent to 0 mod 10. Again, I want x to be an integer, base 10 integer, such that, base 10 digit actually, such that this congruence is true. So I come over here where I have a little more workspace. I can play congruence games. This is mod 10 congruence, so 129 and just 9 are the same thing. So 9 plus 3x is congruent to 0 mod 10. By the way, you might think divide through by 3. We don't have any such property, at least yet, that allows us to divide congruences by a number. Add and multiply, yes, but divide, not yet. What else could we do? I can add or subtract, so 3x is congruent to negative 9, but mod 10, negative 9, is the same thing as positive 1. And so now maybe just trial and error. 3 times what base 10 digit is congruent to 1 mod 10? 0 doesn't work. 3 times 1 is 3, that's not 1 mod 10. 2 doesn't work. 3, 4, 5, 6, 7. 3 times 7 is 21. That is congruent to 1 mod 10. And so x equals 7 is the mystery digit that works. So not only can ISBN detect errors, like if I had put a 6 here, then I would have gotten an incongruence and been flagged as an invalid ISBN. But occasionally, like this, I can even recover what the digit was if I am just missing 1. And last example for now. Question, is 9 to the 100th power minus 1 divisible by 10? So 2 ways to do the problem, the brute force way and a more clever way. The brute force way is to compute this 9 to the 100th power, subtract 1, and see if it's divisible by 10, that is, see if it ends in a 0. Not something I'm interested in doing by hand. Let's recast this a little bit. It's the same question. Is 9 to the 100th power, minus 1 congruent to 0 mod 10. That's what it takes to be divisible by 10. Now, 9 to the 100 are just a bunch of 9s multiplied together. So I can replace any of the 9s by something that they are congruent to mod 10. And there are various ways of doing that, but note, for example, that 9 squared, which is 81, is congruent to 1 mod 10. So in this 9 to the 100th, I have a lot of 9 squareds. And anytime I have a 9 squared, that's just 1. So the computation could go like this. 9 to the 100th minus 1 is the same thing as 9 squared to the 50th minus 1, properties of exponents. And now since we're working congruent mod 10, I can replace the 9 squared by 1 to the 50th minus 1. But direct computation, 1 to the 50th is a much nicer thing to compute. And so answer to the question, since 9 to the 100th minus 1 is congruent to 0 mod 10, 10 in fact does divide 9 to the 100th minus 1. And we are done. Properties of congruence can greatly simplify some types of arithmetic divisibility questions that we want to answer. And we'll stop here. Thanks.